Hello, everyone. Welcome to the second lecture, which is what is statistics? So in this lecture, we will cover a definition of statistics, the two branches of statistics, what data is or data are. Technically, data is plural, but I put the is since I'm referring to a definition of data. And finally, distinguishing the difference between statistics and parameters, populations, and samples. So how do we define statistics? Some people call it the science of data. It's not a bad definition. Problem is it's more of a catchphrase. It doesn't provide you with enough information, in my opinion. A couple dictionary definitions will use the term branch of mathematics. I disagree with this. In fact, most of the mathematicians I've spoken to wholeheartedly agree it is not a branch of mathematics. It uses mathematics, but it also uses logic, sampling techniques, visual display techniques, etc. So even though you may encounter this definition, I would say most disagree with it. So here's a simple definition. The science or practice of collecting, managing, and interpreting data. I prefer an analogy. For me, statistics is like a toolbox with a set of tools in it. And it has two different sides. It has a descriptive side with certain tools, and it has an inferential side with certain tools. And so, as you can see, the core of this class is going to be data. That is what we're interested in, variables and data, and what we can do with this data, how we can organize the data, how we can use data to make decisions, and so forth. So for this class, I'm going to stick with a set of tools that allow us to use data to make informed decisions. And it can do that by allowing us techniques to collect and organize and present and summarize data, to estimate what exists in the population from sample data, make predictions about future events, etc. So this definition, of course, is not comprehensive, but to me, it's a simple, easy to understand definition. And again, the key focus on this class is using data. Statistics, so if we go back to my analogy of the toolbox, you could say statistics is a toolbox with two sides. And on one side, we have a set of tools that allow us to describe the data that we have. And on the other side, we have the inferential branch or inferential set of tools. This allows us to go beyond the data that we have. So with descriptive statistics, you can organize the data that you can have, you can summarize or describe the data that you have, you can picture the data that you have, but you never make inferences beyond the data that you actually have. With inferential statistics, that's the goal. You are inferring something about a population that you don't have or some future event that has not occurred based on sample data that you currently have. So it's going to rely heavily on probability and sampling distribution. So on the descriptive side, some people remember the four basic things that we can do with the acronym COPS. We have tools for collecting data. Ideally, we would like unbiased representative data, especially if we're trying to make eventually some statement about the population. Organized data. Sometimes we have just an unmanageable amount of data. And organizational techniques such as frequency distribution tables and so forth can allow you to manage large amounts of data nice and discreetly, or easily, I should say. So makes it more manageable. Finally, we've got picture our graph. I think you're familiar with that. And so we'll cover techniques for graphing our data, such as pie chart, histograms, scatter plots, etc. And then finally, tools for summarizing our data. You're probably familiar with these, such as the mean and the median and mode, standard deviation, variance, etc. On the inferential side of things, we have tools that allow us primarily to do two things. One is to estimate. So how many people currently have COVID? There's no way to know that because there's no way to simultaneously sample or measure 330 million Americans. So instead, we sample, hopefully it's a representative sample, a few thousand perhaps, and based on that, estimate what exists in the population. Do we currently know what Congress's approval rating is? No. Again, we can't interview 330 million Americans. We take a sample, hopefully it's a representative sample, and based on that, we estimate what exists in the population. We infer what exists in the population based on the sample data that we have. Or we can use our data to predict how many people will there be in the United States in the year 2040. We don't know, but using current models and so forth, we can usually make a decent prediction. They're not always that good, but that's a primary function of inferential statistics. So estimating what currently exists in the population that you don't have for whatever reason, is too costly, too time consuming, too large, or predict some future outcome. Who's going to win the next presidential election? What will the economy look like in 2 years, etc. So for me, statistics is a toolbox with two different sides. We've got a set of tools that allow us to collect, organize, picture, or present, summarize, and then on the other side, the inferential side, estimate, or estimation and prediction. Just a different visual. If it helps you, you could fill this in if you want with some of the things that we have. We're going to go over sampling techniques. We'll go over frequency distribution tables, lots of different graphs, measures of dispersion and central tendency and kurtosis and skewness. And we'll touch a little bit on this. We're going to discuss hypothesis testing and point estimates and interval estimates, but that's really largely for a second class in statistics. So what is data, or what are data? Again, data are plural, so technically when you're referring to your data, you're saying the data are. But I put is because I'm saying, well, what is a definition of data? So variables yield data. And of course, a variable is anything that can assume more than one value. Height, weight, distance, time, your sex, your marital status, political preference, religious preference. Right? And then the observations we make from that, those are our data, or the measurements that we make. So I define data as simply the measurements or observations of a variable. That's it. Typically, especially for this class, the data is going to be represented as numbers, numerical data, but you don't have to have numerical data. It could be non-numerical. In the next lecture, we're going to go over a lot more detail on how to classify, categorize the data that we have, such as quantitative versus qualitative, continuous versus discrete, the 4 scales of measurement. Quick fact, a lot of people like to make a distinction, and I'm not going to worry about it in this class, between data and information. And data and information technically are different. Data are without context. So for example, if I tell you got a 55 on a test, that's simply a fact. That's a numerical quantification. But without any context, you don't know if that 55 is good or bad. Is it 55 out of 55? How did that do relative to the rest of the test, the class, and so forth? So if I then tell you, hey, your score was the best in the class, and you have an A and you passed my class, I've now taken this data and given it some context, so it's turned into information. So I know a lot of people make a big distinction between data and information, especially in some other fields. For this class, it's not a big distinction that I will worry about. Part of the confusion with the class statistics is that the class or the course called statistics in part deals with statistics. And so what's the difference? So what's the difference between the course and a statistic? So a statistic is simply a summary number computed from sample data. And so samples yield statistics. A parameter is a summary number just like a statistic. The only difference is it's computed from population data. So if I tell you the average age of a Troy student is 25, and I ask you, is 25 a statistic or a parameter? Your answer would have to be, I don't know. The reason you don't know is because I didn't give you enough information. Did I compute that 25 years of age, that summary number, using all of the students currently enrolled? For example, I could go to the registrar and he or she could give me that information. Or did I use maybe a sample, such as my class, and based on that sample, compute an estimate of what the average age is? So if 25 were computed from all, let's say 15,000 Troy students, then 25 would be a parameter because it was a summary number computed using the entire population. However, if I told you that 25 was the average age based simply on a sample, for example, the students in this class, then that 25 would be a statistic. So S&S, samples yield statistics, populations yield parameters. In this class, we'll sometimes use different symbols. For example, the mean can be X bar mu, and that will let you know whether or not it was a statistic or a parameter. We'll talk about that later. Quick review. If you haven't had a research class, or I guess you would have covered this in high school, but I'll cover it just to refresh your memory. A population is a complete set of everyone or everything you wish to study. It does not mean the population of the United States. It doesn't mean the population of Alabama or California. It simply refers to a complete set of everyone or everything you wish to study. So in that case, populations can be large, populations can be small. When I compute a mean for exam 1 test performance in this class, then the 50-something students enrolled in this class, that is my population. And it's a small population of only 55 students, but it's everyone that I wish to include. I don't want to include people from different classes when I compute the mean for exam 1 for my class. And a sample is simply a subset of the population. Ideally, especially when we're dealing with inferential statistics, we want the sample to be as unbiased, to be as representative as possible, meaning we hope the sample looks like the population from which it was taken. And this is where we will discuss sampling techniques, especially random or probability sampling techniques. There's no guarantee a sample will ever perfectly represent the population, but if you have a large sample and you use some type of random sampling technique, you're certainly better off than if you simply used a convenient sample or a non-probability sample. Let's go over a few practice questions, see if you understand where we're going. A statistic is to a sample as a parameter is to a population. We know this is true. Statistics come from samples, parameters come from populations. Inferential statistics allow us to collect and organize data. This is false. These are two primary functions of descriptive statistics. Inferential statistics, the two primary functions are estimation and prediction. So this is false. Statistics is a branch of mathematics. Again, some dictionary definitions will say that it's so, some books will say that it's so. For the purpose of this class and the sanity of most of the mathematicians I know, we're going to say false. It uses math, but it also uses probability, sampling, visual display, etc., logic. Inferential statistics involves prediction and estimation. That's absolutely true. Those are the two primary functions of that side of the toolbox. A sample is a complete set. Right off the bat, we know this is false because this is the definition of a population. A sample is a subset of the population. So this is false. The two branches of statistics are descriptive and inferential. This is false. Descriptive is one branch. You may refer to statistics as inferential, but it's inferential is the second branch. So to make it true, it'd be descriptive and inferential. Data are measurements or observations of a variable. That's all it is. It's a simple definition, but I think it's precise or concise and accurate. Inferential statistics never go beyond the data. This is false. That would be descriptive statistics. Inferential statistics, the very function is to go beyond the data that you actually have to estimate something in the population or to predict some future event. So this is false. With inferential statistics, you are inferring something about a sample. Well, with inferential statistics, you certainly are inferring something. The problem is you're not inferring something about the population or the sample. You have sample data. You're trying to infer something about the population that you don't have based on sample data. So this is false. Statistics yield samples. Sounds good because we've got the S and the S together, but statistics would come from a sample, not the other way around. So that's why it's false. And that is it for this first lecture. As always, feel free to text, call, email, or schedule a Zoom meeting.